morning. Welcome to the session on file management in operating systems. So these are the following things we will be discussing in this video. In file management topic, so what is file system structure? What is file system implementation? What is the directory implementation followed? What are the allocation methods followed in file management? What is the free space management techniques followed in file management? How the efficiency and performance of files are maintained? How the loss of files are recovered. All these things comes under as one of the responsibility of operating system covered in file management topic. These are the objectives of this particular video. So what is a file system structure? So whatever files we are storing in a system, that is going to occupy a secondary storage or permanent storage, and how it is being structured and organized and retrieved and it is worked comes under the file management concept, or it is the one of the responsibility of your operating system. So we will see what is, as a first concept, we will see what is a file system structure. So how your file structure, it is nothing but you are not going to keep a rack and you are not going to arrange physical files over there. It is not going to occupy a physical presence. So it is going to occupy a logical storage unit. The first thing, your file structure is nothing but it is a logical storage unit. Collection of related information. That is what we call as a file with respect to a computer or with respect to a system. Logical organization, and what is organized in a logical way? Collection of related information. Then what is file system? File system resides on secondary storage disks. So as I said first, you are going to store your files in the secondary storage disks. That there exists or there resides a thing called as file system. What is the purpose of file system? It provides user interface to storage, mapping logical to physical memory. So there are some files kept in the secondary storage. It has to be brought into the main memory or primary memory for its execution. So there should be some way of mapping which file should be brought to main memory currently. That is achieved with the mapping of logical memory with the physical memory. Logical memory is the secondary memory and physical memory is the primary memory where your program or file is going to be executed. This mapping is achieved by the file system, as well as it provides a user interface to the secondary storage. To access from the secondary storage, it acts as an interface. Then it provides efficient and convenience access to disk by allowing data to be stored, located, retrieved easily. So using this file system only, it provides efficient and convenient way to access the files, store the files, retrieve the files. Okay. Then disk provides in-place rewrite and random access. In your secondary storage disk, it has a in-place rewrite. So in-place rewrite means overwriting of the files can take place. Similarly, it permits random access. Input-output transfers performed in blocks of sectors. So when you have a disk, hard disk, it permits rewriting operation and it permits random access operation, and whatever input output device transfers taking place will be taking place in the blocks of sectors. So your disk will be divided into blocks and blocks will be in turn divided into sectors, and this sectors is where it is the location where your I/O transfer will take place. What is the size of a sector in a disk is each sector will contain a size of 512 bytes. Next one is file control block. It is a storage structure consisting of information about a file. So I said what is a file system, where you are going to access the file from the disk, and there will be a file control block storing information about the files kept in the file system. It acts as an index of that particular file. Then device driver controls the physical device connectivity to your files. Then file system is organized into layers. Your file system is going to be organized in layers in the disk. So your layered file system structure is shown as a reference here. How your application programs, it is going to be accessing, or it is going to be stored as a logical file system, and using the file organization module, then basic file system, then input output control, then devices connectivity. This is how your files will be organized as a layered file system. Then various file system layers we will see one by one. Your device drivers are nothing but it manages the input output devices at the input output control layer. Commands like read drive 1 cylinder 72 track 2 sector 10 into memory location 1060 means read from drive 1. You take the cylinder 72, track number 2, sector number 10, and it has to be mapped with the memory location 1060 in the physical memory. Outputs low-level hardware specific commands to hardware controller. Okay, the purpose of this particular instruction or command is outputs low-level hardware-specific commands to hardware controller. Then basic file system, given command like retrieve block 123 transfers to device drivers. Also manages memory buffers and caches. Allocation, freeing, replacement, all this takes place by the basic file system. It holds buffers, hold data in transit, caches hold frequently used data. So it is the role of basic file system. Next one, file organization module. It understands files, logical address and physical blocks. Translates logical block number to physical block number. Manages free space, disk allocation. This is the role of file organization module in the file system layer. Then logical file system, it manages the metadata information, that is, translates the file name into the file number, file handle, location by maintaining file control blocks. Then directory management, then protection. All these are handled by the logical file system layer. Layering is useful for reducing complexity and redundancy, but adds overhead and can decrease performance. Translates file name into file number, file handle, location by maintaining file control blocks. Logical layers can be implemented by any coding method according to the OS designer. Many file systems, sometimes many within an operating system. File systems can be exams or UFS, FFS, FAT32, NTFS. All these are some of the names of the file systems. More than 40 types of file systems are available. With extended file systems used for distributed file systems operations. Some of the new things are ZFS, Google FS, Oracle ASM, Fuse are some of the new file systems. So till now we saw what is a file system. We saw what is file structure, what is file system, then we see file system implementation. We have system calls at the API level, but how do we implement their functions on disk and in-memory structures? So we are going to use the file system implementation via boot control block. It contains info needed by the system to boot OS from that volume. Needed volume contains OS, usually first block of volume. Next one, it has a volume control block. Super block or master file table contains volume details of the files. Total number of blocks, number of free blocks, block size, free block of pointers or array, all these are kept in the volume control block. Next, directory structure organizes the files. Names and inode numbers, master table files, all these are maintained in the directory structure. Next, per file control block. For each file, separate file control block will be maintained. It contains many details about the file. What are those? Inode number used in Unix operating systems, permissions, size, dates. NTFS stores into a master file table using the various file system structures. What are those NTFS information is? File permission, file dates, create, access, write, file owner, group, ACL, file size, file data blocks or pointers to file data blocks. In-memory file system structures. What are the in-memory file system structures? Mount table storing file system mounts, mount points, file system types. Some of the examples are given for in-memory file system structures in the diagram. User space, kernel memory, secondary storage, user space, kernel memory, secondary storage. So directory structure, file control block, data blocks, all are kept in the secondary storage structure. Or you can have a per process open file table, system wide open file table, index for reading the files. All these structures are called as in-memory file structures. Next concept, partitions and mounting. Partition can be a volume containing file system, just a sequence of blocks with no file system. Next, boot block can point to boot volume or bootloader set of blocks that contain enough code to know how to load the kernel from the file system, or a boot management program for multi-OS booting. Next one, root partition contains the OS. Other partitions can hold other OS's other file system or can be mounted at boot time. Other partitions can mount automatically or manually. These are some of the partitions you can have. Then at mount time, file system consistency is checked, whether all the metadata is correct. If it is so, then add to mount table, allow the access. Next one, virtual file systems, VFS. Virtual file system VFS on Unix provide an object-oriented way of implementing file systems. VFS allow the same name system called interface to be used for different types of file systems. So another concept called as virtual file systems separates file system generic operations from implementation details. Implementation can be one of many file system types or network file system. Implements vnodes which contain inode or network file details, then dispatches operation to appropriate file system implementation routines. The API to the VFS interface rather than any specific type of file system. So VFS contains the file system interface, then the VFS interface, file system type 1, type 2, remote file system, then comes your secondary storage disk. Like this, your virtual file system can work. How to implement virtual file system? Linux has four different, we are taking an example called as Linux operating system as four distinct object types: inode, file, superblock, dentry. VFS defines set of operations on the objects that must be implemented. So every object has some operation to be done. Every object has a pointer to a function table. Function table has addresses of routines to implement that function on that object. Some of the examples are shown here for the various functions are pointers to the function table. The next one, directory implementation. So in directory implementation, it is going to keep a linear list of file names with pointer to the data blocks. It is simple to program, time consuming to execute. Using directory is simple to program but time consuming to execute. Takes a linear search time, and the search time will be more to access a particular file from the directory structure. Then the directory implementation can be done with a linear list. So linear list has some advantages and disadvantages. Next one, it's a hash table concept. So here you are going to maintain a hash data structure. It decreases the search time. It has collisions sometimes when you have two file names of the same location. It is good only for fixed size. Okay. So directory implementation can be done with linear list and hash table. Both has certain advantages and certain disadvantages that we saw in the previous slide. Next one, file allocation methods can do in contiguous manner. An allocation method refers to how disk blocks are allocated for files. How we are going to allocate disk blocks for files. Contiguous allocation means each file occupies set of contiguous blocks. So what are the disadvantage of contiguous allocation? It provides best performance. It is simple. Only starting location is required and length is required. What are the problems of contiguous allocation? Finding space, contiguous space for file, knowing the file size, external fragmentation. All these are some of the disadvantages for contiguous allocation. So mapping from physical to logical to physical. Logical memory address 512 Q1R. So the directory showing the file name, the length, starting block and the length of the block. Block to be accessed equal to Q plus starting R address. Displacement into block, we call it refer as R. So a contiguous allocation means you are having a continuous allocation of the memory space. Sometimes it is difficult to find continuous memory space. Next, extent based systems. Many newer file systems have been coming. They are using modified contiguous allocation scheme. An extent is a contiguous block of disks. Extents are allocated for file allocation. File consists of one or more extents. Next one, linked allocation. So in contiguous we saw an example, extent based systems. Next one, linked allocation. Here each file, a linked list of blocks are allocated. File ends at nil pointer, no external fragmentation here. Each block contains pointer to the next block. No compaction, external fragmentation is there. These are the advantages. Free space management system called when new block needed. So that the free space management gives the new block and that can be connected to your linked list. It improves efficiency, but the disadvantage here is increases the internal fragmentation. Reliability can be a problem. Locating a block can take many input, output or disk seeks. So locating a file may be difficult in linked allocation. Example for this is FAT, file allocation table variation is based on linked allocation. Beginning of volume is table indexed by block number. It is like a linked list but faster on disk and cacheable. New block allocation is simple. In case of FAT, so each file is a linked list of disk blocks. Blocks may be scattered anywhere on the disk. It is one of the advantage. You don't need to find a continuous memory space. Block to be accessed is the qth block in the linked chain of blocks representing a file. Displacement into block equal to r plus 1. Here file G starting address is 9, starting block is 9, end is 25. So 9, the connectivity shows 9, and from there it is 16, and from there it is 1, and from there it is 2, and from there it is minus 1. It indicates the end over there. And your FAT example shown here. So you have the file name test. Starting block is 217. Goes and accesses the 217. It finds refers to 618 block. Again that goes there. There it refers to 339. Here it is a link to each block number. From there 339 is accessed. To get your file test as shown in the directory entry. Next type of allocation is indexed allocation. Each file has its own index blocks of pointers to its data blocks. Example of indexed allocation. Again it shows the directory structure for the file G. The index block is 19, so it go and refer the 19. From 19, again it shows 9, 16, 1, 10, 25, minus 1, minus 1, minus 1. So corresponding blocks are taken. Okay. So it need index table. It permits random access, dynamic access without external fragmentation, but has the overhead of index block. So here again mapping of logical to physical in a file, maximum 256k bytes and block size of 512 bytes. We need only one block for the index table. Q is displacement into the index table, R is displacement into the block. Mapping from logical to physical in a file of unbounded length. It is a linked scheme, link blocks of index table. Can also be done in linked allocation. Okay. Two-level indexing can also be used. Outer index, index table file. So two level of index can be used also in indexed allocation. Next, in Unix UFS file system, they are using a combined scheme for file allocation. 4K bytes per block, 32-bit addresses. More index blocks than can be addressed with 32-bit file pointer. So a diagram showing how indexing is followed in Unix UFS file system. Performance. Out of the available allocation methods, which is having a best performance? Best method depends on the type of file access. Contiguous is great for sequential and random file access. Linked is good for sequential and not random access. You have to decide whether which access type, and based on that you have to decide contiguous or linked allocation. Index is more complex than the above two allocation methods. Single block access could require two index block reads, then data block read. So here indexing is going to be complex for file allocation methods. The other overhead is you have to see the index table allocation also. That is an overhead here. So example to show the index, example to show the performance is given here in an Intel Core i7 Extreme Edition. Next topic is free space management. So how to utilize the maximum free space in the disk. So our file system maintains free space list to track available blocks clusters. Then bit vector or bitmap is used to manage free space management. Suppose 1 equal to block I free, 0 indicates block I is occupied. So you are using the bit vector. So if the bit 1 is given, that means block is free. If the bit is assigned to 0, then the block is occupied. Block number calculation. Number of bits per word is followed by the formula number of bits per word star number of zero valued words plus offset of first 1 bit. CPU have instructions to return offset within word of first 1 bit. So bitmap requires extra space. That is the disadvantage here. For example, block size equal to 4 KB, that is 212 bytes. Disk size is 2 power 40 bytes, that is 1 terabyte. Then n equal to 2 power 40 by 2 power 12, which is 2 power 28 bits or 32 MB. Clusters of 4 blocks, then 8 MB of memory is required. Easy to get contiguous files based on bitmap. Linked free space list on disk. Second technique is linked free space list on disk. Linked list of free list cannot get contiguous space easily. So what they are doing, no waste of space here. No need to traverse the entire list. If a number of free blocks are recorded. Another technique, grouping. Modify linked list to store address of next n-1 free blocks in first free block plus a pointer to next block that contains free block pointers. Next technique is counting. Because space is frequently contiguously used and freed, with contiguous allocation, extensor clustering, keep address of first free block and count following free blocks. Free space list as entries for addresses and counts. Next one, space map technique. It is used in ZFS file system. Consider metadata of input-output on very large file system. Full data structures like bitmaps couldn't fit into memory, so they are using space maps. Divides device space into metaslab units and manages metaslabs. Given volume can contain hundreds of metaslabs. Each metaslabs has associated space map. Uses counting algorithm but records to log file rather than the file system. Log of all block activity in time order is recorded in space maps. When it comes to efficiency and performance of the free space management technique, disk allocation and directory algorithm. Efficiency is based on disk allocation technique and directory algorithms. Types of data kept in the file directory entry. Again, it depends on pre-allocation or allocation of metadata structures. It also depends on fixed size or varying size data structures. Performance. So efficiency depends on these factors listed there. Then performance depends on keeping data and metadata close together. Buffer cache. Separate section of main memory for frequently used blocks. Synchronous writes, sometimes requested by apps or needed by OS. No buffering or caching. Writes must hit disk before acknowledgement. Asynchronous writes more common, bufferable faster. So these are the performance factors to be considered when it comes to file management. Next, page cache. What is page cache? A page cache caches pages rather than disk blocks using virtual memory techniques and addresses. Memory mapped I/O uses page cache technique. Returning routine I/O through the file system uses buffer disk cache. Input output without a unified buffer cache. Memory mapped I/O use page cache. I/O using read and write use buffer cache. And the buffer cache will access the file system. Unified buffer cache means it uses the same page cache to cache both memory mapped pages and ordinary file system I/O to avoid double caching. But which caches gets priority and replacement algorithms to use. So I/O using unified buffer cache. So you are using buffer cache along with file system. Recovery, if there are any damage to the files, how to recover. So that is done with the following concepts. Consistency checking. Compares data in directory structure with data blocks on the disk and tries to fix inconsistency. Here comparison of directory structure and disk blocks are done. Can be slow and sometimes fails. This is how you can recover inconsistency checking. Then use system programs to back up data from disk to another storage device. This can also used for recovery of files. Recover lost files or disk by restoring data after data from the backup. So this is another way of recovering files. Log structured file system. Log structured or journaling file system record each metadata update to the file system as a transaction. All transactions are written to a log. A transaction is considered committed once it is written to the log, sometimes to a separate device or a section of disk. However, the file system may not yet be updated. The transactions in the log are asynchronously written to the file system structures. When the file system structures are modified, the transaction is removed from the log. If the file system crashes, all remaining transactions in the log must be still performed. Faster recovery from crash removes chance of inconsistency of metadata. So log structured file system recovers files like this. Example, NFS Sun Network File System. An implementation and a specification of software system for accessing remote files across LANs. The implementation is part of the Solaris and SunOS operating system running on Sun workstations using an unreliable datagram protocol and Ethernet. An example file system is described in this particular style.